In this video, I will teach you about higher order derivatives. Consider example 1. Find the first, second, and third derivative of y equals 4x to the third power plus 3x squared plus 2x plus 1. Now, the first derivative is just the good old-fashioned derivative that we've been learning about for the past few videos. So we're just going to take the derivative of each term one at a time. So for the first term, we'll use the power rule and bring the 3 out front to multiply by the 4, so that'll make 12. And we reduce the power by 1, so we've got 12x squared. Moving on to the next term, power rule again, 2 times 3 is 6. Reduce it by 1, it'll just be x. Moving on to the 2x. The derivative of 2x is just going to be 2. And then the derivative of a constant is always going to be 0, so we write nothing. So this is the derivative of function y, and we could call it the first derivative. Now, the second derivative is what you get if we take the derivative of the first derivative. So we will denote that y double prime. And the second derivative will work like this. If we do 2 times 12, that makes 24. We're just doing the power rule. Decrease by 1, and it becomes 24x. Moving on to the 6x, if we take the derivative of that, that'll just be 6. The derivative of a constant is 0, which we write nothing. So this is the second derivative. Now for the third derivative, which we will denote y triple prime, you get the third derivative by taking the derivative of the second derivative. So starting with the derivative of 24x, that's just going to be 24. And again, the derivative of a constant is 0, so we write nothing. So here we have the first derivative, the second derivative, and the third derivative of the original function y. Here's one way that higher order derivatives apply to the real world. If s at t is a position function, then the first derivative, s prime at t, will be a velocity function. And the second derivative, s double prime at t, will be an acceleration function. In other words, if you take a position function and take the derivative of it, you're going to get a velocity function. Now, if you take a velocity function and you take the derivative of that, you have an acceleration function. Because the moon has no atmosphere, a feather and a rock will fall at the same rate. If you drop them both from an initial height of 2 meters, their height is given by the position function s at t equals negative 0.81 t squared plus 2, where s at t is the height in meters and t is the time in seconds. Find a function for the velocity of the objects at time t. Well, if you want to find a velocity function, the velocity function is going to be the derivative of the position function. So if we take the derivative of this, we're going to have to take the 2 and multiply it by negative 0.81, and that's what's going to go in the front. That turns out to be negative 1.62. When we reduce the power by 1, it'll just be t. The derivative of a constant is 0, so we write nothing. So that's it. The velocity function is negative 1.62 t. Next, we must determine the acceleration due to gravity on the moon. Well, acceleration is the derivative of velocity. Or you could look at it as the second derivative of the position function. Either way, we're just taking the derivative of this. When you have the derivative of a constant times the variable, it's just the constant. So the acceleration due to gravity is negative 1.62 meters per second per second.